So hello everyone, we'll start the today's session. So in today's session, we'll be seeing the contents of week 8, which is the hydrologic analysis. And before that, we'll be first seeing what is slope area method, which is a part of the streamflow measurement from the week 7 content. And we'll be moving on to the hydrologic analysis. And in hydrologic analysis, we'll be seeing different kinds of problems, how to solve uh, the problems related to the unit hydrograph. So we'll be seeing how to derive a unit hydrograph from a given direct runoff hydrograph, and we'll see the other way around. So direct runoff hydrograph will be given, and we need to derive the unit hydrograph. So we'll move on to the theory of slope area method. So this slope area method is more related to the hydraulics part. So, but anyway, it's a part of the streamflow measurement. So we can just quickly go through and solve a numerical. So the slope area method is based on the law of conservation of energy, and in this method, what we do is we select some cross section across the river, and this cross section geometry we already know it beforehand. So here I am representing the cross section of longitudinal section of the river in between these two cross sections. So 1 and 2 are the two cross sections, and we represent the channel base, and we have a datum head, we have the depth of water y1 and y2, and as the water flows from one section to the other section, we have the energy loss associated with it, and they have two kinetic heads, v1 square by 2g and v2 square by 2g, and this total head loss is a function of two components. One is the head loss due to friction, and other one is the eddy loss. So what we will do now is we will apply the energy equation across these two sections. So from the basic principles, we can write the energy equation in cross section 1 and 2. So we can write datum head plus your depth of water plus your kinetic head u1 square by 2g should be equal to z2 plus y2 plus v2 square by 2g plus your total head loss. Now we need to we'll bring the head loss to one side, and rest of the components will keep it on the other side. So we'll be writing z1 plus y1 minus z2 plus y2 plus v1 square minus v2 square divided by 2g. So we can represent z1 plus y1 as h1, which represents the stage, which has a reference to your mean sea level or your data. So I am going to write z1 plus y1 as h1, which is nothing but the stage, and z2 plus y2 as h2. So this is h1 minus h2 plus v1 square minus v2 square divided by 2g. Now, as I said earlier, this head loss is a function of two components. So one is the head loss due to friction, plus another one is the head loss due to eddy. So we'll now equate both the equations. So hf plus he is equal to h1 minus h2 plus v1 square minus v2 square divided by 2g. So for head loss, we have a standard expression. This has been derived. So head loss is given as Ke into V1 square minus V2 square divided by 2G, and need to consider the modulus of this value. And here Ke is 80 head loss coefficient. Now we need to determine what is the head loss due to friction. That is the component which we want for this particular question, this particular method. So HF is equal to H1 minus H2 plus V1 square minus V2 square divided by 2G minus HE. And we can represent the flow rate by using the Manning's formula in the open channels. So by Manning's equation, we can write Q is equal to A by N R to the power of 2 by 3 into S to the power of 1 by 2. So in this, if you see, we can write R as A by P to the power 2 by 3. So in this equation, if you see, your area, your perimeter, and your Manning's coefficient, all three are constant. We can group them together, and we can write them as a single constant term, which is represented by K. So here K stands for the conveyance of the channel. And if you see from the diagram, we can represent the head loss due to friction with respect to the slope. So if L is the distance between the two sections, then we can, by using tan theta, we can write the slope as for small theta, we can write tan theta is approximately equal to your bed slope. So we can write S is equal to HF divided by L. And the conveyance K is a single parameter which will be used in the equation to solve the questions. So since we have the properties of two sections, what we'll be doing is we'll take the geometric mean of the conveyance. So your k, which is the geometric mean, is given by k1 plus k2, square root of k1 plus k2 for 2 sections. And for n sections, we can write them as k1, k2, k3, so on up to kn. And we need to take the nth root of it. Now how to solve this equation? So if you see the equation, let me write the equation once again. h1 minus h2 plus v1 square minus v2 square divided by 2g minus h. So if you see this equation, so q is a function of your head loss due to friction, and hf is a function of velocity, and we can write velocity as a function of discharge also. So it is a kind of a loop. So this is a kind of a endless loop. So we cannot solve it directly. We need to use iteration. So we will assume some initial value of velocity, and we have v1 also and v2 also. So this is what we'll be doing. So we know the stage, and from the stage we know what is the, we can calculate the discharge through that particular section at that instant of time by using the Manning's formula, and we can determine the velocity. So from that we'll be assuming that the velocity is equal in both the places, and we'll be iterating the solution. We'll be solving for HF, and after solving, we will see whether the discharge is converging or not. Once the discharge converges, we'll stop the iteration and we'll proceed and we'll finish the problem. So now we'll be seeing one problem related to this method. So the question says that in order to compute the flood discharge in the stream by slope area method, the following data was obtained. So they have considered here three sections, and the geometrical information of the section is already given. So they have given the area wetted perimeter, and in these two, in the upstream and the downstream section, they have measured what is the uh, stage of the river. And now we need to determine what is the flood discharge, assuming that the Manning's N is 0.029 and the length between the upstream and the downstream section is 250 meters. So first, and this is a question which was asked in engineering service uh, in the year 2000 mains exam. So first, let us represent the three sections as 1, 2, 3. So the upstream section, downstream section as 3, mid section as 2. So we need to compute the conveyance of the sections first. So we saw that K is equal to A by N R to the power of 2 by 3. And your R is nothing but A by P. So first what we will do is we will compute the hydraulic mean depth, which is R. That is 108.6 divided by 65.3. That is 1.663 meters. A2 by P2, which is 99.80 divided by 59.40, 1.680 meters. Next is R3, 103.1 divided by 60.7, that is 1.669 meters. So now we can compute the conveyance. K1 is equal to 108.6 divided by Manning's coefficient multiplied by 1.663 to the power of 2 by 3. So similarly, K2 and K3 we can find out. So after computing the conveyance, now we are going to take the geometric mean of it. So K here will be K1 into K2 into K3 to the power of 1 by 3. And if we compute that, we will get 5058.07 meters. So now in the first iteration, assuming V1 is equal to V2, and now we will be using the head loss due to friction, that is H1 minus H2 plus V1 square minus V2 square divided by 2G minus KE into the modulus of it. So since V1 and V2 are same, HF will be simply H1 minus H2. HF is equal to 316.80 minus 316.55, which is equal to 0.25 meters. Now from the discharge equation, this is nothing but head loss due to friction, right? So this is the equation which we derive. So we can compute the discharge now. This is 5058.07. This is 0.25, and the distance between the cross section is 250 meters. So and now this is equal to 159.95 meter cube per second. Now we have a estimated discharge. So by using the continuity equation, we can determine the velocity of the section 1 and 2. So this will be Q by A1, and V2 will be equal to Q divided by A2. So we can determine Q1 and Q2. Now in the next iteration, we'll be using these two velocities instead of assuming v1 is equal to v2. So we move on to second iteration. So we'll stop the iteration when the velocity does not vary much with respect to the previous iteration. So similarly in the second iteration, Ke can be taken as 0.1. So now we'll be using the h1 minus h2 is 0.25 plus 1.47 square minus 1.602 square divided by 2g, which is 2 into 9.8 minus 0.1 into modulus of 1.47 square minus 1.602 square divided by 2 into 9.8. So now HF will be equal to 0.2269 meters. So again we can find out what is the discharge. This is 5058.07, 0.2269 divided by 250. So this will be 152.30 meter cube per second. So now we can determine V1 and V2. So now we can see the velocity with respect to the previous iteration. So they have a very big variation. So we can do one more iteration. So HF in this case is 0.229 meters, and we can determine Q again. So we can find out V2. So with respect to the previous iteration, the velocity is more or less similar. So let us do one last iteration and we'll see what is the result. Just to be sure. So this is 1.4 meter per second. So with respect to the previous iteration, the difference in the velocity is more or less similar. So we can stop the iteration, and the final discharge what we estimated was Q is equal to 153.252 meter cube per second. So this is the quantity of water that is flowing in the river. So given the cross-section properties and value of stage, we can estimate what is the flow rate that is passing through the river by using the slope area. So next part of the session is the hydrologic analysis. And this topic is one of the most important topic for any of the competitive exams. And here we'll be seeing the method of unit hydrograph. So what is unit hydrograph? So unit hydrograph can be defined as a direct runoff hydrograph that results in a runoff depth of 1 centimeter in a catchment. So this is like so you have a rainfall that happens for duration d hours, but the magnitude of the rainfall is such that your runoff depth is only 1 centimeter at the catchment outlet. So this is Q and this is T. This is the unit hydrograph. So this is nothing but runoff depth is equal to volume under DRH divided by the area of catchment. This runoff depth is equal to 1 centimeter. So let's say this is a DRH. So if you compute the area under this curve, that will give you the volume of runoff. So this is area under DRH and this is. So there are two important assumptions. One is the time invariance. It is that for a given effective rainfall, which can happen at any period of time, your unit hydrograph will not change. This is the first assumption. The second assumption is the linear response. So any change in the input is reflected proportionately in the output, which is the DRH. So here we have the principle of superposition. And the principle of proportionality. So what I'm going to do here is I'm going to kind of like give a working rule, like how to approach a problem, because people tend to make mistakes by reading the question in a hasty way. So I'm going to explain two working methodologies, so which you can follow while solving the problem. So that will not make you confused, like you'll be knowing what you are doing. So let us say that you have been given a rainfall of 3 hours, that duration of 3 hours, and the magnitude is 1 centimeter. So the resultant of this in a catchment will be a 3-hour unit hydrograph. So because it has the excess rainfall of 1 centimeter that is happening. So this is nothing but a 3-hour unit hydrograph. Now if you want to obtain a flood hydrograph, a flood hydrograph is the combination of your base flow, your unit hydrograph multiplied by the precipitation value. Excess rainfall value. So this is nothing but a flood hydrograph. Let's say that we want to obtain it for a 3-hour rainfall with excess rainfall as 5 centimeter. The procedure to be followed is when you have the unit hydrograph, you can multiply it with the excess rainfall. So multiply the ordinates excess rainfall. So in this case, you will be doing multiplication with 5. So the resultant will be a so this is again 3 hours, but since we have multiplied it 5, this magnitude is 5 centimeters. And what we will be getting is, we will be getting the direct runoff hydrograph. So your unit hydrograph will look something like this. Now what we have to do is, we need to add base flow to this DRH, and the resultant will be a flood hydrograph. So now we'll see the second approach. So depending on the problem, you'll be dealing with either approach 1 or approach 2. Now let us say that you have 2-3 hour duration, and the rainfall excess is 1 centimeter again. So in this case, how your unit hydrograph will look is, for the first 3 hours, you will have a unit hydrograph, and for the next 3 hours, this unit hydrograph will be lagged by 3 hours. So I'm using a term called lagging the hydrograph. So this is lagged by 3 hours, and this is the time axis, and this is the discharge axis. Now what will happen is, if you lag it and then add it up, you will get a DRH of 6 hours with rainfall excess 2 centimeters. So this is a unit hydrograph, and this is also a unit hydrograph, which is giving a excess rainfall 1 centimeter each. and when you add up, you are getting a direct runoff hydrograph for a 6-hour duration with rainfall excess as 2 centimeter. So this is a 6-hour duration, and this magnitude is now 2 centimeters, and you have your DRH. So maybe turn this as 6-hour DRH. Now we need to convert this into a 6-hour unit hydrograph. So for that, what we will do is we will divide this DRH by the 2 centimeters. So here what we will do is the DRH ordinates divided by 2. So the resultant will be so this is 6R, but the rainfall excess is 1 centimeter now. And this is your 6-hour unit hydrograph, and your DRH will look something like this. Now we need to obtain a flood hydrograph. With rainfall excess 7 centimeters. So if the rainfall excess is 7 centimeters, we need to multiply the ordinate by 7. So what we will get is 6 hours, but the rainfall excess is 7 centimeter. So it will result in a 6-hour DRH of rainfall excess 7 centimeters. Again, to obtain the flood hydrograph, we need to add the base flow to it. Now here we need to add base flow to all the ordinates. So now let's move on to the different problems. So first question is, the ordinates of a 4-hour unit hydrograph is given, and we need to determine the ordinates of a 8-hour unit hydrograph by the method of superposition. So first given is 4-hour unit hydrograph. We need to convert to 8-hour unit hydrograph. So in this we'll be seeing this approach 2, where you have been given a 4 hours. If we lack the 4-hour unit hydrograph by another 4 hours and add it up, we'll get a 8-hour unit hydrograph. So let us see how to do that. So we can form a table for this. It will be easy to work. Time and 4-hour unit hydrograph ordinate, which is given in the question. So this is meter cube per second. per centimeter of rainfall excess. So 0, 4, 12, 16. So this is given in the question. Now what we are going to do is we are going to lag this unit hydrograph coordinates by 4 hours. So what I mean by lag is we'll first leave the first column as empty, and this entire time series we are going to write it down here again. 0, 20, 80, 130, 150, 130, 90, 52, 27, 15, 5 and 0, and we add 4 hours extra. So that is our time base of the 8-hour unit hydrograph. Now we have lagged it. Now what we are going to do is we are going to add it up. So this is unscaled 8-hour DRH with 2 centimeter excess rainfall. So for this we are going to add this column in this column values, sum it up and then write it here. So this will be 0, 20, 100, 210, 280, 280, 220, 140, 71, 42, 20, 5, 0. Now we need unit hydrograph, so we are going to divide it by 2. So this will be 0 by 2. And so on, we need to keep dividing. So this is the 8-hour unit hydrograph. So this is one type of question. It's very direct and straightforward. So the second question, your watershed has an area of 777.6 square kilometer. The response of the watershed to a unit rainfall excess is in the shape of a triangle with the base time as 72 hours. With the peak discharge occurring at the 25th hour, we need to determine what is the peak discharge of the watershed. So what they are saying is the unit hydrograph for this particular catchment is in the shape of a triangle. So we'll first draw that. So this is the unit hydrograph, and they have given the time base as 72 hours. So this is the time axis and this is the discharge. And we need to determine what is the peak discharge of this particular catchment. And they have told that this peak discharge occurs at 25 hours from the start of the start of this graph. So this is like a simple ratioing only. So we know that rainfall excess is equal to area under DRH, which gives the runoff volume, divided by area of the catchment. So since this is a unit hydrograph, the rainfall excess is 1 centimeter. So I am converting it into meters for the uniformity of units. And we need to determine the area under the DRH. Here it is the area under the unit hydrograph, which is nothing but half into base is your time base, 72 into 3600. I'm converting the 72 hours into seconds, into height. Height is the peak discharge, divided by area of the catchment is given as 777.6 square kilometers. I'm converting into the appropriate units. So your QP can be estimated as 16 meter cube per second. So let us move on to the next question. So the third question is, ordinates of a 6-hour DRH is given with an effective rainfall of 3 centimeters. Now we need to determine what is the 12-hour unit hydrograph by the method of superposition, and if the effective rainfall intensity is in the catchment occurring for two successive 6-hour duration or 1 centimeter per hour and 0.5 centimeter per hour, then we need to find out the DRH ordinates for the storm occurring over the catchment. So this is another kind of question which you will be facing. So here they have given DRH, and we need to determine 12-hour unit hydrograph, and this DRH is for 6-hour duration. So first thing is we need to lag by 6 hour and divide by 2 centimeters. And the second part of the question, effective rainfall intensity is given, and we need to find out. So this effective rainfall is given for two storms, and we need to determine what is the complex storm direct runoff hydrograph. So in the question we have the time ordinates that is given for a 6-hour direct runoff hydrograph. So this goes from 0 to 48 hours. and the corresponding DRH ordinates. This is in meter cube per second. This DRH corresponds to a rainfall excess of 3 centimeter. So first what we will do is, we will find out the 6-hour unit hydrograph. So for that we need to divide the DRH ordinates divided by 3. So 6-hour unit hydrograph, this will be meter cube per second per centimeter. So this will be 0 by 3, this will be 30 by 3. And we can continue for all the time steps. Now we need to find a 12-hour unit hydrograph. For that, what we will do is, we will lag the 6-hour unit hydrograph by 6 hours. So for lagging, first column will be blank and the rest will follow the time series. So this will be here, this will be here. Next we need to find out the unscaled 12-hour DRH. So for that we need to add these two columns. So this corresponds to a rainfall excess of 2 centimeters. So this will be 0, 10, 50. Now we can finally find out what is the 12-hour unit hydrograph. So this will be in meter cube per second per centimeter. So we will divide the previous column value by 2. So this completes the first part of the question. And the second part, what they have given us, they have given an effective rainfall intensity. So we can draw the hydrograph for that. So for the first 6 hours, we have an excess rainfall of, so this is effective rainfall intensity, I am terming it as ERI. This is in centimeter per hour. So this is 1 centimeter for first 6 hours and 0.5 centimeters per hour for the next 6 hours. So from this we can determine the excess rainfall depth, which is nothing but effective rainfall intensity multiplied by the duration. So for the first 6 hours we have 6 centimeter rainfall excess, and in the next 6 hours we have 3 centimeter rainfall excess. Now we need to find the DRH for this complex storm event. So we have two precipitation events that are happening, and it has produced two different types of rainfall excess. Now we'll see how to approach this kind of problem. So again I'm writing the time ordinates. And we have the 6-hour unit hydrograph ordinate from the previous calculations. Now we need to find out what is the direct run of hydrograph for the first event. So this is DRH for precipitation event 1. So I'm going to multiply the unit hydrograph ordinate with the rainfall excess, which is 6 centimeters. So this will be 0 into 6, this will be 10 into 6, and we can continue. Now next step is to find out the DRH for the second event. But the second event happens after 6 hours. So before that we need to lag the unit hydrograph by 6 hours. So I am going to lag the second column by 6 hours. So it will be 0. So I am bringing it here. So once we lag it, we can now determine what is the DRH for the second event, which has a excess rainfall of 3 centimeters. So I'm going to multiply it by 3. So this column will be blank, then 0 into 3, this will be 10 into 3, and so on. So our aim is to find out what is the combined effect of these two events. So we are going to add up the red columns together. So that will give you the DRH for complex storm. So this is with respect to how to find out the unit hydrograph for a complex storm. So next we'll be seeing one more different type of a question. So for in this question we'll be using the discrete convolution equation, because here the question is direct runoff resulting from a successive 2-hour duration of rainfall excess values of 2 centimeters in the first 2 hours, and in the next 2 hours we have a 4 centimeter of rainfall excess, and we need to determine what is the 2-hour unit hydrograph from this catchment. So here we are not given with the unit hydrograph, but rather we are given with the direct runoff hydrograph. So we cannot use the principle of superposition or the principle of proportionality to find out the 2-hour unit hydrograph. Rather we will be using the convolution equation in this particular question. So since DRH is given, and the catchment has a complex storm, 4 centimeter and 2 centimeter and 4 centimeter. In successive 2-hour duration. We cannot determine the so the discrete convolution equation is given by Qn is equal to, that is the hydrograph of ordinate of the nth time interval, is a summation of m varying from 1 to n, and this should be less than or equal to m, Pm into un minus m plus 1. So here Pm is the rainfall excess, and Qn are the DRH ordinates. So in this particular equation, the successive equations will be increase the u by 1, increase the rainfall pulse by 1, and decrease the hydrograph ordinate by 1. So that is, if you want to write for Q1, we can simply write as P1 U1. But if you want to write for Q2, we will increase the precipitation unit by 1, and So for the first time step, we'll be writing P1 into U2, and for the second term, we will increase the P by 1 and decrease the U by 1. So similarly, we can keep writing like this for n time steps. So this will be P1 U3 plus P2 U2 plus P3 U1. But in the question, we have only 2 rainfall pulses. So this term, we don't have any precipitation value. So this term will vanish. So in a similar way, we can write for n number of ordinates. But we need to determine how many number of ordinates are possible with this complex storm. For that, in the table, we have been given so we can determine the number of unit hydrograph ordinates as n minus m plus 1. So here, this is n, this is m. So it will be 11 minus 2 plus 1. That will be 10 ordinates. So we need to write the equations for Q1 to Q10. And this is nothing but your Q is nothing but your DRH value. So for the first equation, 0 is equal to P1 is 2 centimeter U1, which is equal to 0 meter cube per second. And for this, the second value in the table is 100 meter cube per second. That should be equal to P1 is 2 centimeter, U2 we have to find out, plus P2 is 4 centimeter, but U1 is 0. So we can find out U2 as 50 meter cube per second. So similarly for Q3, we have 2 times U3 plus 4 times U2. So we'll be making successive substitutions from the previous step. So U3 will be equal to 125 meter cube per second. Similarly, we can write for Q4. So that will be P1 U4 plus P2 U3. So rest of the term will be 0 because we don't have P3. So this will be 2 times U4 plus 4 times U3. So from this, we'll get U4 as 75 meter cube per second. Similarly, Q5 will be P1 U5 plus P2 U4. This will be 2 U5 plus 4 U4. That will be 70 meter cube per second. P1 U6 plus P2 U5. This will be 2 times U6 plus 4 times U5. It will be 50 meter cube per second. So after this, if we plot the variation of the DRH, so this is 0 and it goes on until 20 hours. And this is your discharge, meter cube per second per centimeter. So this will be the kind of variation in the unit hydrograph. So this is the 2-hour unit hydrograph. But in the rest of the questions, it will be something like this. So you have a DRH and you will convert that into a unit hydrograph. Then you will multiply that unit hydrograph according to the magnitude. Let's say for the first event you have this much, and for the second event which starts 2 hours later, the magnitude is smaller. And then when you add it up, your DRH will look something like this. But here it is not the case, because we have been provided with a direct run of hydrograph, not a unit hydrograph. So this is in the usual case. But in this case it is quite different. So we'll see the next two questions. So the fifth question is similar to the second problem which we saw earlier. So here the catchment has an area of 50 square kilometer, and phi index is given as 0.5 centimeter per hour. During a storm event, it was observed that the catchment has a base flow of 10 meter cube per second, and for a rainfall of 1 centimeter, excess rainfall of 1 centimeter, the time base of the triangular hydrograph was found to be 15 hours. So this is nothing but the unit hydrograph which they are talking about. Determine the peak discharge of the catchment. Suppose if the total storm depth of 5.5 centimeter happens over the catchment for 1 hour, then what is the peak flood discharge? So we'll see how to approach this question. So here again they have given a triangular unit hydrograph. And the time base is given as 15 hours. The catchment area is given as 50 square kilometers, and base flow was observed as 10 meter cube per second, and phi index for this catchment is given as 0.5 centimeter per hour. Now first question is to determine what is the peak discharge of this particular catchment. So this is Q and this is Q. So we have seen already rainfall excess is given by area under the direct runoff hydrograph or the unit hydrograph divided by catchment area. So in this case, this is a unit hydrograph. So the rainfall excess is 1 centimeter. I'm converting it into meters. And area under the DRH is the area of the triangle. Half into base is 15 hours. Converting it into seconds. And multiplying by 3600. Into height is the peak discharge which we need to find out. Divided by catchment area is 50 square kilometer. And I'm converting it into meter square. So from this, if we compute, the peak discharge is found to be 18.52 meter cube per second. So this is the first part of the question. Now what they are saying is that now if precipitation of magnitude 5.5 centimeter happens, what is the peak of the flood hydrograph? So first for that we need to determine what is the rainfall excess for a precipitation of 5.5 centimeter. So to determine the rainfall excess only, we have been provided with the phi index. So the rainfall excess is P minus phi t. So rainfall excess is equal to 5.5 minus 0.5 into 1. So the rainfall excess is 5 centimeters. So for this rainfall excess, we need to determine what is the Q flow. So we know the ordinate of the unit hydrograph is 18. So this is per centimeter. 18.52 multiplied by 5 plus base flow. Base flow is 10. So your flood hydrograph is a combination of your direct runoff hydrograph and your base flow. So that is the one thing which you need to remember in this question. So now let us move on to the last question for the day. So the direct runoff hydrograph for a river draining a catchment area of 189 kilometers square due to isolated storm with a uniform intensity, has the shape of a triangle with a base time of 66 hours and a peak coordinate of 32 minutes, occurring at 10 hours from the start of the DRH. Now we need to develop a 6-hour unit hydrograph for this particular catchment. So the given information is area is 189 square kilometers and base time of the DRH is 66 hours and peak discharge is also given 30 meter cube per second and time to peak from the start is given as 10 hours. Now we need to determine the 6-hour unit hydrograph coordinates and the DRH unit hydrograph representation. So let us first draw a triangular hydrograph. So this is 30 meter cube per second. It's the DRH. So this is 10 hours, this is 56 hours, the total time base is 66 hours. So first we need to determine the runoff excess, rainfall excess. Again, area under the DRH divided by catchment area. So this will be equal to half into base is 66 into 3600 into 30 meter cube per second divided by 189 into 10 power 6. This will give in terms of meter, but we need it in centimeter, so I am multiplying it by 100. So the rainfall excess will be 1.885 centimeters. So from this DRH, we can determine the coordinates of the other time steps by using the method of similar triangles. So we can find out the other coordinates, time in hours, DRH coordinate in meter cube per second, and UH coordinate. So this is nothing but DRH divided by rainfall excess. This will be meter cube per second per centimeter. So for convenience, I am taking the coordinates at every 6 hours, but it is not compulsory to take it at every 6 hours. It can be even less than that or even more than that. So just for convenience, I'm taking it for every 6 hours. And by similar triangles, we can compute for every 6 hours what is the value. And we are dividing this by 1.885, which is the rainfall excess. So now we can plot and see visually how does it look. So that you'll be able to determine the differences. So first I'm drawing the DH. Next I'll draw the unit hydrograph. So they both have the same time to peak as well as time base. So this is 15 hours, this is 0 hours, this is 66 hours. And we can also represent the rainfall that happens for a duration of 6 hours. So your time to peak will be 7 hours. So this is 20 meter cube per second. This is 15.92 meter cube per second. And this is the 6 hour DH. And this is the 6 hour unit hydrograph. So this is how you represent as graphical. So that's it for today's session. I hope this is useful for you in the competitive exams. Thank you.